Computational Finance Group. We welcome you to this monthly seminar, which is the aim is to bring the new research in quantitative finance to an audience of quantitative academics. We are thankful to our sponsors, the Citibank and Mosaic Smart Data, for allowing us to have this very nice seminar series here. So now I'm going to pass the floor to my colleague Blanca, who's going to introduce our speaker today.
Yeah. First of all, I'm very happy to have so many of you here. I'm very happy to welcome Kevin Webster, who has a very extensive career in many aspects. Currently, he is at Imperial College in a visiting position, and I'm not sure if we can say the next step after that.
Nope.
Not yet. Okay, we can't. But we're very happy to have him here. And if you have seen, he's author of several books that you have seen on display in the launch area. So if you would like to have a look afterwards, after the talk, please go ahead and ask Kevin for the details. The title of today's talk is Getting More for Less, Better A/B Testing via Causal Regularization. Kevin, the floor is yours. Maybe a quick thing, if you want to ask questions, I have to come to you with the microphone, so just raise the hand and I'll be with you.
Thank you, Blanc. Thank you, Rama, for the kind invitation, and thank you for hosting me. So this is a talk about separating alpha from price impact in trading using randomized trading experiments. And we called it cheekily Getting More for Less, because a key point of the talk is that randomized trading experiments are costly. They tend to be small. And so we'd like to get as much mileage out of them as possible. So this is based on joint work with my co-author, Nick Westre, who works at Alliance and Bernstein and who's also associated with NYU. And you can find the paper on SSRM. So as a quick motivation or introduction, I'd like to just give a couple of definitions. And so price impact is a core concept in the talk. So I just want to clarify my definition of price impact. So I define price impact as a causal model for trading, meaning when I talk about price impact, I talk about returns, about price moves that are caused by my trading. Meaning in a parallel universe where I choose not to trade, the return will not happen. This is opposed to an alpha signal where regardless of whether I choose to trade or not, the return will still happen. And another way to think about it is in terms of backtesting. If you have a prediction signal and in your backtest, you're going to assume that no matter what, that return prediction will happen, regardless of whether you trade faster, slower, or whether you don't trade at all, then it's probably an alpha signal. However, if you think the market will have some kind of reaction to your trade, then it's a price impact model. And again, this is useful for backtesting. So here this is a very simple simulation. So I take a historical price path where I've traded a certain strategy, and I ask the question to my price impact model, what if I traded faster? What if I traded slower? Economists call that counterfactual analysis. And so if I have an alpha model, the answer is the same thing. I'm just replaying history. But if I use a price impact model, then I will get different answers. If I try to trade faster, the market will react by pushing up the price. This is a scenario where I'm buying. If I choose to trade slower, then I will have a lesser reaction from the market. So I would, in this case, get this blue line there. And eventually all these things revert back as I stop trading. Price impact models are commonly used by practitioners in a couple of applications, but probably the most important one is optimal execution and transaction cost analysis, which are two sides of the same coin. One of them is ex ante or during trading, minimizing transaction costs, and the other one is ex post, analyzing whether you've actually optimally executed an order. So I'll just give a quick quote by Berchel van Racklen, two senior managers at Alliance and Bernstein, an American fund. So in 2013, they used their proprietary trading data to fit price impact models for TCA applications. And so in that paper, they say practitioners use impact models as a pre-trade tool to estimate the expected transaction cost of an order and to optimize the execution strategy. So this talk is going to be quite heavily related with TCA. And so I just wanted to give, this might not be I want to give an example of a TCA report for people who have not seen it. So I actually expect most of the audience to have seen TCA reports, but just to fixate some ideas. This is obviously a mock TCA report. It's way smaller than the pages and pages that you would get with many breakdowns across algorithms, across trading venues, across assets. But generically, what traders look at in these TCA reports, or clients of brokers, is they want to look at breakdowns so they can analyze and compare different trading strategies in different market environments. They look at obviously how orders were allocated to these different buckets and strategies. And then the first order concern is the order slippage. How much did the order slip compared to, say, their arrival benchmark? So you typically have a column there with some confidence interval. And after that, you have a lot of explanatory columns that try to explain the performance of the algorithm. So here I picked some examples. You might look at spreads and fees that you pay to different venues. And a column that shows up pretty quickly is some kind of decomposition of whether the price move happened because of the trade, so that would be price impact, or whether the price move, whether you could have done something like accelerate and capture more alpha in the trade. So I call that alpha slippage. Again, this is a mock example, and there are many more columns and many more rows that you could have in such a report. But this is for illustration purposes. So now, the main scenario I want to describe in this talk is the point of view of a broker who executes orders for a client and who is tasked both for TCA purposes and optimal execution purposes to estimate the price impact of their client's orders. And this isn't quite equivalent to just measuring this order slippage. The reason for that is that clients don't submit random orders. They actually expect to make money out of these orders, and therefore they tend to trade based on some kind of alpha prediction. And that's good for the client. They want to capture the alpha. But that's unfortunately a confounder for the broker. When they measure the slippage, they don't really know if it's alpha, the client's alpha, or the price impact of their trading algorithm. I'll quote my ex-boss, Daniel Nairn, on this. In his book, he says, large-scale trading will often occur in the presence of market drift, alpha, and the realized cost is a combination of alpha and the price impact. Now, I've been harping about this distinction between alpha and impact. Why does it matter?
Well, sorry.
Yep.
Also volatility.
Yes, also volatility. Because you care about execution risk as well. So if I say in a risk neutral world, then I mostly care about alpha and impact, but I completely agree. If you have any kind of risk constraint, then you would care about volatility as well. So why do I want to distinguish between alpha and impact? Because my action set is different, depending on whether I think slippage is due to alpha or impact. In the same paragraph, Daniel explains it, I think, more eloquently than me. If we find that most of the cost is due to price drift, aka alpha, the best option would be to accelerate the trading and pay more impact to capture more attractive prices. Conversely, if the cost is mostly driven by impact, then it would behoove us to slow down our trading to minimize the impact. I accentuated the point the last time, and I promise I'll leave you alone with this, but the same return prediction, so in both cases you predict that the price is going to go up, you take diametrically opposed actions depending on whether you think that same return prediction is due to alpha, aka exogenous to your trading decision, or is due to impact, aka endogenous to your trading decision. Okay.
But actually, your former boss doesn't say alpha; he says price drift.
Yes, but
more accurate because it could be due to vol.
That is true. That is true. I agree. I guess there's, yeah. In the equation, I guess that would be the last term here. impact alpha, and then the noise term, which would have the vol. So, so the talk is also called Disentangling Alpha from Impact. Jean-Philippe Bouchot gave a name to this problem. He called it prediction bias, and he phrases it as the difficulty in establishing whether a trade causes a price move or anticipates a price move. I'm going to instead quote Rob Almgren, seminal work in price impact in 2001, and also co-founder of Quantitative Brokers. So he understands these things reasonably well. And so he stated, impact cannot actually be disentangled from alpha due to the endogeneity issue. It is not possible to work out if the order caused the move or the reverse. So just to highlight two reasonably big people in the field saying that this is a hard problem. And indeed, we'll show, it's a trivial proof, but we'll show that without additional data, just looking at past history of trades, without some kind of labeling mechanism or some kind of randomized trading experiment, you just cannot distinguish the two. There's just nothing you can do. You need something else. So yeah, we'll see what that is later, but essentially it's randomized trading experiments. So I'm going to give some toy models before I go into my machine learning algorithm. But so imagine you believe the true world to be return equals impact plus alpha plus some noise. So lambda of fq, q is my trade size, f of q could be linear, square root, whatever your favorite impact model is. Again, it could be much more sophisticated. It could depend on trading speed, on ADV, market cap. The point is it's a function of your order. So that would be my price impact. And then alpha is my predictor of the price. Could also be a function of all kinds of features, news data, events, earnings, all these kinds of things. And then again, some noise. If you knew alpha, then you could fit impact in a bias-free way. You just compute alpha-adjusted returns, do a linear regression, and that would give you your impact model, and there would be no prediction bias. However, that requires you to A, observe the alpha, and B, reproduce it historically. So the first one is the case I'm more interested in, because as a broker, you're very unlikely to be given the alpha by your client. They just don't like giving it to you. But even if you're in a fund, it's still hard, because imagine you are inside a fund, but trading for discretionary portfolio managers. They don't give you a number. They just, based on their human decision, decide to trade. So then that's still a difficult problem. You're not really given in a quantitative manner the alpha. Even if you're in a quant fund, alpha models change, infrastructures change. This is more of a technology challenge, but sometimes you just don't have access to the historical alpha. Somebody threw away the code. And so you can't really do this method. So this is another quote just to say the obvious: traders are understandably reluctant to pass their alphas over to a broker due to the potential for lost intellectual property, front running, etc. So what do you do when you're missing a key component of the model? Traditionally, what you do is you just do the regression without it, maybe with an intercept. Unfortunately, even with an intercept, this regression will be at some level biased, because Q and alpha are fundamentally correlated. The larger your alpha, the larger the trade. Therefore, when you do this regression, this lambda here will be an overestimate of the true price impact of the trade. And an intercept won't help with that. I mean, it'll help a little bit, but it won't completely fix the bias. Because again, if you have an intercept, you capture the average alpha, but you still have the problem that higher alpha trades will still give higher, larger orders, and therefore that correlation is not captured by a model like that. So if you just do a linear regression ignoring the hidden variable, you'll just get a biased estimate. So that's my introduction. Now, what am I going to do in the talk? First, just because I'm a mathematician, I want to formalize a bit this concept of prediction bias. I want to prove as generally as possible that there isn't some secret machine learning technique to magically remove this bias from historical data alone. So that's going to be using do calculus, but again, I'll go, the technical details don't really matter. Then I'm going to introduce the missing ingredient, which is randomized trading experiments. So think of broker wheels where you randomly assign to different brokers, all kinds of experiments. So I'll introduce a particular experiment that I'm going to simulate. I'm going to, in a simulation environment, create thousands of copies of dozens of different experiments to compare them. Because I have now the simulation environment where I can test different experiment designs, I can compute confidence intervals of these methods, and I can compare them. In particular, I can then propose my own method that hopefully will be better than just using naive randomization. So that will be this causal machine learning technique called causal regularization, which is very simple. And finally, in the last section, I'll compare it. I'll do the actual empirical analysis and compare the performance of these models. All of these comparisons are in a pure simulation environment. It uses market data, but in a simulated environment, meaning I replay the tape and then I simulate price impact. I know the ground truth because I literally add my price impact to the historical data. I don't actually do live trading experiments. So obviously that is a possible criticism of the paper, but also we'll see that even if you do live trading experiments, you still want to complement it with simulations because otherwise it's very hard to get confidence intervals unless you're willing to run a lot of live trading experiments. Before I go into technical details, just a sneak peek at the conclusion. So at the end, what I'm going to compare is basically three methods using the historical trading data without looking at randomized trading data. And so that will be this first row here, method A. So randomization size 0. I will use no randomized data, just historical data. And that's going to be fundamentally biased. So for, I think in this case, it's the Almgren model from 2005, but for very realistic price impact models and for very realistic execution schedules, I think in this case it's VWAP, you get about 30% bias. And again, this is in a simulation environment where I know the ground truth. But you're very confident. You're very confidently wrong. So that's what happens when you don't have any additional information. Now, method B is to only use the additional information, to only use the randomized trading experiment. There's an argument to be made for that. The randomized trading experiment is the only one for which I know for sure that it is unbiased. I throw away all of that biased data. It's worthless. And so that method will give me always an unbiased estimator, but for small randomization sizes, I'm not going to get a grade t-stat. I'm going to be not very confident, but at least I'm going to be unbiased. And so the idea behind causal regularization is maybe I can reintroduce the historical data. Maybe I don't have to throw it all away. I have to acknowledge the fact that it's biased, but maybe I can combine in some intelligent way the biased historical data, which is very large, and just correct it with the unbiased randomized data. And what you get is something that's unbiased, but has a little bit of a better confidence interval, at least for small sizes. Eventually, as you make the experiment grow in size, the observational data, or sorry, the historical data doesn't add any value anymore because you already have enough data in the unbiased sample set. So the benefit is biggest for small experiments. Okay, so early takeaway, again, I'll repeat these points, but causal regularization essentially will use up about 5 times as little randomized data to come to similar conclusions. And we think it has applications in all kinds of trading problems, but just to give some examples, a broker who is trying to estimate price impact not knowing the client's alpha is kind of our canonical example of an application. But you could do the opposite problem, which is I'm an alpha researcher at a fund. In theory, I know my trading data because I get it back from my broker, but maybe I don't fully trust the data. Not that I don't trust the broker, just they collect their data in a certain way, and I prefer my data in a different way. How can I estimate the alpha of my trades without relying on the broker's price impact model or trading data? So that's a problem that you can tackle. So it's the inverse problem essentially, and then more generically, broker wheels or any kind of situation where you randomize a trading decision to figure something out, limit order placements, order cancellations, these kinds of otherwise very intractable problems. And yeah, so now I'm going to jump into the actual details. So if you remember this, there's going to be 4 sections. The first section is just proving that there is a problem. So this is going to be mostly math. And I'm going to first motivate why I'm using math, or why I'm using specifically causal inference. So causal inference is a theory that was developed in the 90s in statistics and computer science departments, initially to tackle a completely different set of problems. And it was very successful. Rubin, one of the 2 main leaders in the field, concluded in 2004. Fortunately, the days of statistics can only tell us about associations, and association is not causation, seem to be permanently over. Now, that doesn't contradict the usual motto of like correlation is not causation. Correlation plus something equals causation. The plus something is quite important. But if you have something, you can actually prove things. And it's been recently coming back to the foreground in the tech industry. Because of concerns about model robustness and generalizing models outside of their training sample. So it's a big field. Not going to go through these quotes. I know I like to quote a lot, but what I'm trying to convey here is that Microsoft made it its major topic in 2021. Netflix made it one of its core principles. Uber, Meta. Before LLMs were the big hot topic, causal inference was, and I still think it's still pretty hot, but just not, obviously not ChatGPT levels of priority. This quote I will give because I like it a lot. So Uber gave a technical paper where they describe in reasonable detail their infrastructure. So it's not a math paper, it's a computer science paper of how they build their infrastructure to field requests for randomization and do the analysis on top of that. And in the paper, they also have a section about why they did that from a business perspective, what argument they used to justify this very heavy infrastructure sell to their stakeholders. And I like it because I think you could copy paste it for TCA and it just works beautifully. So this is for Uber deciding how to charge you for, when the weather is bad, how much to charge you extra. They randomize and then they decide how much they can charge you. But I think this applies to TCA, or at least to my interactions with traders and brokers quite well. The results are universally trusted, allowing teams to align on the ground truth quickly and act on it without endlessly reinvestigating surprising findings, rerunning faulty experiments, and second-guessing decisions. I would love for my TCA system to like have that level of confidence. So they just invested quite a fair bit to at least project that level of confidence. Okay, now mathematically, how does this work? How does causal inference work? It's actually quite simple. If you remember probability 101, omega FP, you have a probability space, measurable outcomes, and a probability measure. Well, in causal inference, the extra ingredient is a causal graph. And all a causal graph is for all the random variables that you care about, you just say what's a cause and what's an effect. And that forces some independence assumptions. So if 2 nodes are disconnected, then they have to be independent, for example. Things like that. So here's the very simple graph I proposed for our problem, the prediction bias problem. I have the features that drive my alpha model, call it the earnings data or whatnot. And so those features that drive also the stock price. So I have an arrow from alpha to returns. And then I believe in price impact. So I have an arrow from trades to returns. I believe that when I trade, I get a feedback from the market. I cause changes in the market. But here's the key point. I don't believe that Q and alpha are independent. I have a link between them. And specifically, I have a link from alpha to trades. I believe that my clients, because they have alpha, submitted the trade.
Sorry, I have a question here.
Yes.
Here you need to carefully distinguish predicted alpha and realized alpha.
I agree.
Because it's the predicted alpha.
It is the predicted alpha, absolutely.
And it may not be realized, especially if you have a full mark.
I completely agree.
You need to be double.
Absolutely. So in my simulation environment, I know the 2 are perfectly in line because I control the alpha. I'll get to in my simulation. But I completely agree. In real life, you need at least 4 nodes. You need alpha predicted and alpha realized.
Kevin, would you mind repeating the question for me?
Yes, Rama's question was how I have only one variable here called alpha, but in practice, people distinguish between predicted alpha, ex ante, what do I think is my prediction? So I think the price is going to go up by 20 basis points. And the realization, which is obviously much noisier. And if my alpha model is incorrect, I might think in expectation I have 20 basis points, but actually I don't. And so to Rama's point, it doesn't actually matter if the alpha is correct. It matters that it drives the trades. So the alpha here is the predicted alpha, not the realized one. Yep, go ahead.
That's true for the vertical arrow.
Yes.
But for the arrow from alpha
Yes.
to delta P, that's the realized.
Yes.
So
ideally,
it's
I would
more
have.
complicated.
I completely agree with you. The ideal graph would have 4 nodes: alpha predicted to Q, alpha realized to delta P, and then some connection between alpha predict and alpha realized. I'm definitely. This is more of a toy model in the sense of in my simulation environment, I can guarantee that the predicted and the realized have correlation, are highly correlated. But I completely agree with you. If that correlation is low, I should not have one node here. I should have 2 correlated nodes. You still get the back path though. The key point is you get confounding from this. When I try to measure Q to delta P, the correlation is driven not just by this link here, which is what I want, it's also going through some backdoor path. And that will still be true for the correct model, which is the one that you described.
The other remark is, is Q really the only driver of delta P? There's, if
The
you're
speed.
single agent.
Yes, you could have the trades from other people. I can expand this model quite a bit. Actually, in my book, I have an expanded model with crowding. So where you say my alpha, other people have it as well, and they also have price impact. And that obviously makes the confounding even more complicated because now I'm measuring my price impact or the price impact of the people copying my alpha. So this is a toy model. In my simulation environment, I can guarantee that this toy model is correct because I control everything. But for these more complicated scenarios where I suspect that my alpha is crowded or that my client's alpha is crowded, you could expand the methodology. I just don't do that here. But I appreciate that these are all valid concerns, extensions, practical thoughts. Thank you for the questions. And so, again, it's a trivial result, but the vocabulary of causal inference is quite nice for it. So if you've not seen do calculus, expectation of return given do Q is the actual estimate of this link, not the correlation between returns and trades. It's just how it's defined. It's defined as the true causal link as opposed to the correlation. And so in do calculus, you often want to prove that either an estimator is biased or unbiased. You want to show that this equality either holds or doesn't hold, meaning looking just at historical data, looking just at historical correlations, do I recover the true causal mechanism? Now, why do I do this level of generality rather than just proving that the linear regression data is incorrect? That would be a much easier proof than this very general proof. The reason is in this fancy math statement, it's just more general. It says for any probability measure consistent with the causal graph. What this means is that there's no amount of fancy machine learning techniques that will fix this. This is a property of the data. You need new information. You need something else, some kind of new data, either labeling or literally new data, new rows that have some kind of different property. It is the fact that the estimator's bias is not a problem of linear regression. It's a problem of the data. So again, I appreciate that this is, if you haven't seen do calculus, this looks like mumbo jumbo, but the word statement is important. There's no amount of fancy neural networks that's going to fix your data issue. And in that sense, Amgren is completely right. Without additional information, you cannot disentangle alpha from impact. You need something. So that something is randomized trading experiments. Well, that is one of the things that you can use. There are other things, but that's the one I'm going to investigate. Just to highlight that this is not a hypothetical thing. Again, in the paper, we do it in a simulation environment, but these are live trading experiments are things that you can do in practice. So Deutsche Bank mentions that they use controlled A/B experiments on a subset of their orders, so they segment a part of their orders to really quantify their impact. I like that quote because it makes it explicit that they only do it for a subset of orders because it's expensive. Another example would be CFM that did a long-array experiment. So they really want to check if their impact is any different from the rest of the market. Rama and I had just had a discussion earlier today on like this anonymity of trades. Like there's no reason why the market should behave differently from one person's trade versus another person's trade, at least at the short term. But they want to test that. And so they tested that by sending random trades for a whole year, just to measure truly the impact of those trades. And by sending random trades, they were guaranteed that there was no alpha whatsoever, no other confounding, no crowding. These are random trades. They are, by definition, uncorrelated to everything else going on. So these are examples of real-life trading experiments that are related to TCA and price impact. But they're naive in the sense of they throw away all the historical data. So in causal inference terminology, this is what we call the observational data, the data as usual, the biased data. I'm giving synonyms, but again, in that community, in that machine learning community, the terminology I'm going to use here is observational data. It's the data where I don't intervene, I don't randomize. And so we in our simulation environment, we're guaranteed that this is the correct model because that's how we simulate it. In real life, you have to assume that that's the model. And again, to Rama's point, I can make different assumptions. I can talk about crowding, I can talk about realized versus historical alpha, but this is by model for my observational data. And then when I randomize, what happens is I cut this link. I now have that Q and alpha are not correlated anymore. I don't trade based on alpha. And so that's why on this causal graph here, that do calculus statement becomes true. Expectation of do Q equals expectation of Q, because there's no collinearity anymore between these two variables. But there's a practical issue. Interventional data is unbiased, but it's scarce. You're not going to be able to have a lot of it. And that's going to cause you problems from a confidence interval perspective. So let me give an example. This is basically an example that we simulate in multiple copies, but one instance of our simulation is this example. So I'm assuming that my client is investing in the Russell 3000 and trades about 1,000 trades a day. That leads to 250,000 trades in a year. There's 250 trading days in a year. And so over a period of 10 years, I might have 2.5 million data points. That's actually quite a fair bit. That's a decent amount of data. So my observational data set, the biased one, is big. However, I can't go back in time and randomize historical data. Like if it's biased in the past, it's going to stay biased for forever in the past. So I can only deploy live trading experiments in the future. And so because of that, they will be limited in duration, because not only can I only do them in the future, so if I want the same sample size, I'd have to wait 10 years, but also people don't want to wait 10 years. So they're limited in duration. In addition to that, they're also limited in size, because most people will not want to randomize 100% of their trades. They will randomize a small fraction. So here I picked 3%. So if you randomize 3% of your orders, and if you're willing to wait 2 months, which I think are reasonable, optimistic, but reasonable values, you'd have about 1,000 trades. Enough to do some statistics, but not enough to fit a neural network. Not that you have to fit a neural network, but I'm just trying to convey like the size difference between this randomized trading experiment and this historical data. In addition to that, this is, I don't want to say best case scenario, but it's a moderately optimistic scenario. If you have any kind of multiple experiments going on, they have to compete over the same randomization pool. And so you might end up, if you have 5 experiments that you're running simultaneously, you might only have 250 trades per experiment. Again, enough to compute some kind of, yep.
Are you using the same level of alpha in all of the experimentation you're making?
Actually, so within one experiment, yes, which I'm sure, that I'm essentially assuming some kind of stationarity. We do rerun the experiment with so the nice thing about having a simulation environment is that we can rerun the experiment with different parameters. So we try different price impact models, we try different alpha strengths, but within a given simulation, yes, I assume it's a constant strength of alpha. Does that make sense? I completely agree with you. These are all the confidence intervals I will give you are in that sense best case scenarios, because I'm assuming all the parameters are constant over time. So I'm assuming I have a strong stationarity assumption here. yeah, so definitely something to keep in mind. But also, like, we picked a simulation that's reasonably straightforward. You could make the simulation more realistic. I'll get into the details of simulation in a second. Thank you for the question. So this is the example that is our kind of guiding light. So interventional data, unbiased but small. Observational data, biased but large. So why do we use a simulator? Partly because we don't have access to real life, the ability to run real life trading data as in an academic paper. That's kind of not in the domain. But partly also, even if we did, we would still think a simulator is helpful. Why? Because I'm harping on this point quite a fair bit. Trading experiments are small because they're expensive. And there's nothing worse than deploying a trading experiment and then realizing halfway through that it's poorly designed. It doesn't measure what you want to measure, or it measures it too slowly. You have to start from scratch. You need to either do a larger flow, do it for longer, or use a different data set, maybe a higher alpha, a data set that you suspect is higher alpha, so that it's easier to disentangle the two. Whatever it is, you don't want to, after the fact, realize that you don't have the data you need to do this, to do the statistical procedure. So one way to ex ante realize that your experiment is flawed is by simulating it. By simulating it, you can create not just one copy, but hundreds, thousands of copies and compute confidence intervals. Like, you can ask the question in simulation, I don't know what the mean is going to be, like that beta is going to be based on my ground truth. I can definitely compute how long do I need to wait for before I can get a reasonable confidence interval on my price impact. And that's just very, very useful, just because of the cost of live experiments. And so I really recommend this paper by Kevin Webster. It's a pure methodology paper. I guess ours is as well to some degree. But yeah, it's one that describes how to simulate alphas and orders, realistic orders. Yeah, I'll go through it very quickly just from a reproducibility perspective. I want to be fully transparent here on how we do this. So we start from realized returns, so realized market data. We look into the future, we add some noise, and that gives us an alpha for which we can perfectly control the correlation. This is obviously not an alpha you can implement in real life because it looks into the future. But in our simulation environment, it allows us to simulate an alpha of any strength that we want. If we want a 1% correlation, 5% correlation, 50% correlation, we can have that. And to your point, we could make that vary. We could have very fine control over the ground truth. Now, we don't just care about the alpha signal, we also care about the trade. And so there we set up a mean variance optimization problem because that's how a large number of clients will probably set up their problem, an alpha signal, a mean variance optimization problem, some risk and some trading constraints, and that gives us a way to turn alpha signals into trades. And those trades will be, so we simulate those, and again, we have perfect control over the alpha content of the trade, and we have realistic sizes, participation rates, distribution across, give me a sec, distribution across market capitalization and ADV just by construction, by taking alphas that we perfectly control and putting them into a mean variance optimization problem. Yes, there was a question in the back.
May I ask, when you do the simulation, thank you. May I ask, when you do the simulation, do you assume any distributions?
Yes, so that can be criticized. So when I do the alpha, I inherit the distribution of the realized future returns. So there I'm non-parametric, but I have to add noise. So I think we tried Gaussian noise and something a bit more heavy-tailed, but like that noise level does matter a little bit in terms of the distribution of the errors of that alpha. Put differently, like, yes, I control the correlation, but sometimes you don't just care about the correlation of the alpha, but also the autocorrelation of the alpha and the distribution of the residuals. The point is, we perfectly control that as well. If you want to have, a certain correlation structure, you can. We picked two examples, Gaussian and some heavy-tailed. We never looked at the autocorrelation of the alphas, so we could have controlled that, we didn't. Did that answer your question?
Yes.
No problem. So again, fully transparent, like this isn't a simulation environment. We start off from realized market data, but there's definitely some assumptions that are made here. But it's also fully customizable to some degree. And you could do all of this with your actual historical alphas if you have them, but then you don't have control over how strong they are. Yeah, so that's the input, and then using that, we can now simulate hundreds, thousands of copies of the synthetic alpha and the synthetic portfolio. We're always going to assume that we have 10 years worth of historical data, so that never changes. And then we do different experiments designs, so like different types of statistical methodologies and then different sizes of the interventional data. So ranging from what we think is a realistic but small experiment, a realistically medium to large size experiment, and then kind of not exactly a limiting case, but a case where you start having a lot of interventional data. An expensive experiment, let's put it this way. And we also tried different price impact models just to make sure that the results are robust to that. They're not specific to, say, a linear model or a square root model. And yeah, so I'll give the first two methods, and then I'll talk about our method. Just because the results for the first two methods are also interesting. Like one thing that one added value of the paper is just highlighting that you can compute confidence intervals for randomized training experiments, even if you don't believe in causal machine learning, even if you just do regular randomized training experiments. This is a useful method to figure out ex ante whether an experiment is well designed. So this is just the illustration for if you ignore the randomized training experiment, you just use the historical data. And again, I've shown it before, but you get for this particular alpha signal, so 5% correlation with the future. In this case, it's Gaussian noise. And for the Almgren 2005 model, you get that it overestimates the price impact model by 30%, and it's very confident. So typically, this is what we find in our study. Ignoring the bias just means that you have high bias and low variance. You're very confidently wrong. And then on randomized trades, you always get that it's unbiased, but you get a much wider confidence intervals. And it's kind of natural, but it scales in 1 over square root n, given our assumptions. And yeah, so for small experiments, you might not be quite happy with these confidence intervals. But once you reach a certain amount of data points, then it becomes a bit more valid. And to your point, these are optimistic t-stats and confidence intervals because this is a purely stationary simulated environment. So you probably want to divide these by a certain factor for more realistic scenarios. But in terms of comparison, it's helpful to have a benchmark. So this is the benchmark that we want to beat. But again, even just having some notion of if an experiment is well designed for traditional methods is a helpful tool. So now our method. So this is part 3, and then we're almost there. So what is causal regularization? It's a method that was developed at Amazon for their experimentation design. As I said, tech industry is kind of a little bit, not exactly ahead of us, but like has published some stuff in that domain. So there's 2 papers by Jansik, both in 2019. One is the applications paper, and the other one's the theory paper, the mathematical proofs. So we piggyback off that paper to and apply it to finance. So the idea is really simple. Your unbiased data is too small to do any kind of sophisticated fitting. You have 100 or 1,000 data points. That's not enough to fit anything sophisticated, like even just definitely nothing non-parametric, but even just if you put too many parameters, it will break down. But what you can do is you can treat it as a testing sample, as an out of sample. So the methodology is really fit your model in sample. It will be biased. So, and then use the unbiased data as an out of sample and use regularization to shrink the model. So that way you don't throw away the biased data. You use it for training, but you get through the regularization property, you get the unbiasedness of the testing data. Before I go into why this works, maybe what motivates this use. essentially it's that imbalance in the sizes of the data sets. Typically in samples are much larger than out of samples, and that just happens to be the regime that we're in. In trading we have, as I've been arguing, a lot of observational data and very little interventional data. So we happen to be in the regime where this method makes sense. The reason I mention that is often I get a reaction from people, why doesn't the medical field use this? Why doesn't everybody use this? The answer is they're not in that data regime. Like when you give drugs to people to test their efficacy, it's expensive whether you do it observationally or interventionally. I mean, double-blind randomized experiments are a little bit more expensive, but if you're going to go through the effort of recruiting people to test the drug, you might as well make it randomized. So they're not in that regime. So the reason why the tech industry developed that, and it hasn't been quote unquote invented in fields that have a much longer history of doing causal inference, is because they are also in that regime where they have essentially infinite amount of observational data, but very limited interventional data. So from a, I want to say, business perspective, causal regularization makes sense because of the data regime we're in, which is different from the data regime in, call it, traditional economics and healthcare. Okay, this is the algorithm. I've kind of already spoiled it, but just to write it down. My inputs are observational data, which I assume is large, interventional data, which I assume is small, a model with some kind of parameter, and a regularization penalty. In step one, I'm going to train a family of models on the observational data. It's going to be parameterized by my regularization penalty. So I don't have one model, I have a family of models. This is how regularization works. And then I tune the metaparameter to narrow down that family of models to that one final model. And how do I tune it? I tune it on my unbiased data. So again, it's a pure analogy with regularization. Sorry, that's poor choice of words. With standard regularization, it's just that you use randomized data as out of sample data.
So why do you do 1, 2, and not 2, 1?
1, 2, not 2, 1.
Is 1 a prerequisite for 2?
Yes, you think of it as, oh, sorry. So you're asking why do I use, maybe to repeat the question.
Yeah, so why do you need to do the fitting for all values of lambda prior to using the interventional data set to tune lambda? Because you need to use the output of 1 for 2?
Yes.
Okay.
So the idea is, imagine a scenario where I have a lot of features. Way too many features so think linear regression, but with hundreds of features. For example, you fit non-parametrically, instead of believing it's a square root, you just say, I do a basis function expansion. I have 100 basis functions. You're not going to be able to fit that with 100 data points or 1,000 data points. You could fit it, like with 2 million data points, you can fit that on the observational data, but it's going to be biased. Does that make sense? By doing regularization, by fitting, basically, you're implicitly assuming that the structure.
Maybe, do you have an example later?
Maybe
it's clearer if you give an example.
This is essentially my example, but no, I don't have like an example where I give all the columns in the raw data.
What do you mean by regularization? Are you going to add a penalty with lambda
penalty.
in front of it?
Yes, bridge penalty. Sorry.
So you will have an example.
Yes. So I have So I have a high dimensional data. It's on the training data. I can fit that data, but it's biased by 30%. I know that from the ground truth. And then the regularization will figure that out. It will keep the same structure, but it'll figure out that it needs to level it back down. Does that make sense? And intuitively, that's what a human would do anyway. They would probably look at fitting a price impact model on their data, and then just use the out of sample, the randomized training data to just drop it down by a level. So this is just an automated way of doing that. Yes? Oh.
Hi. So in practice, often things aren't equally weighted. As you put it, you might care about dollar-weighted slippage. So as you say, you have lots of big orders possibly in your observational set.
Yep.
But your randomized testing set is likely to have smaller orders. So how does it make sense where you sort of care about some kind of large orders mostly, right? But then does this work if you're not equally weighted?
So the answer is no, that's a fundamental problem, but that's a different kind of fundamental problem. Like that's a pure sampling problem. This is at that point not a causal problem, meaning I can make that same statement about any method where I sample small things. And so the answer is you either start sampling large orders, even randomized, or you believe your model enough is that when you fit it on small, but like those are obviously the first is better than last, but it's expensive, which makes even more of a case for why you need a good method to deal with small randomizations. Because to your point, we will have way more luck randomizing in this region than that region. So in our simulation, I will admit we sample pretty uniformly, which is definitely a possible criticism of the simulation. But again, I could, if I want to, I can change the simulation to see what kind of confidence interval I would get if I started sampling here less. And what I would expect is even with this method, you get wider confidence interval here. But I get even worse confidence intervals for the not using observational data. Did that answer your question? Yeah. Again, I don't have a magic bullet for that one.
Often with these things, sometimes you zoom in on this area.
Yep, 100% agree. Yep, no, I agree. This does not fix that particular problem. So I said why, from a business perspective, causal regulation makes sense, and that's just that data regime that we typally in trading. Now I just want to very quickly explain why mathematically it works. And essentially in the companion paper, in the technical companion paper, Janzik essentially just mimics the proof in standard regularization. And he just realizes that in that proof, you make very few assumptions about the out of sample. All you assume is that essentially the out of sample doesn't have the same bias as the in sample. So if you think of traditional regularization, you do cross validation. And why does cross validation work? Well, as long as you don't literally use the exact same data as the in sample data, you will not have the same spurious correlations as in the in sample data. But if you look at the proof, there's nothing that says it has to be from the same distribution. It just says it has to not be biased in the same direction as the in sample data. And so essentially, again, he goes through the lines, he goes through the proof line by line, but essentially it's a proof by analogy. Yes.
Wondering, in terms of the regularization, are you penalizing the sort of difference between the randomized data and the observed data, or are you penalizing something else?
No, I'm just shrinking it. It happens to work in this case because I know that the true model is smaller. Does that make sense? So obviously the prior matters quite a fair bit. Implicitly, a regularization penalty is always a prior. So in a weird world where I would be biased the wrong way, shrinkage would not be able to get me there. Does that make sense? But in our case, we already know. Like if you're a human, so like somebody, you can see this as just automating a human process that already exists. If in the observational data, you get, let's say, lambda of 1, and then on a randomized training data, you get 1.7. You know that 1.7 is wrong. Why? Because you know the observational data is biased upwards. There is no world where the observational data, which has way more data points, gives a smaller number than the true number. So to some degree, you could throw away all the machine learning. As a human, you could literally just say, I min-max between 0 and the observational data, and that's already a better estimator because it's a shrunk estimator. Does that make sense? And that's what the prior gives you. And regularization is just implementing a prior. Your prior is that the observational data that the observation is pretty good, but that you are smaller than it. That's what the regularization gives you. And again, a lot of this is at the intuition level is just implementing what humans would already do, which is they do a randomized trading experiment, then they look at the observational data, and then if there's a mismatch between the two, you throw away your randomized trading experiment, or you correct it, if that makes sense. This is to some degree what the method does.
Yes, thank you.
No problem. So this is kind of the summary I gave earlier. So you can get a better t-stat for less data, which is kind of nice. I don't know how much time I have left.
We're getting towards the end.
Okay, perfect. So there's other applications. I mentioned them earlier, and this was meant to be more the appendix, or in case I went through things too fast, but you can do the converse scenario of if I'm an alpha researcher and I want to estimate my alpha without using broker data or broker impact models. I just don't trust the broker's impact model. It's fitted on somebody else's data. I'm special. Every alpha researcher thinks they're special. Then you can do essentially the same thing. You just randomly not submit trades, measure the alpha on those, and then you can't just do that because that's too expensive. Not submitting trades, you can't just not submit 20% of your flow. But with causal regulation, maybe you can not submit 4% of your flow and still get a reasonable estimate of your alpha. And it's model-free estimate of your alpha, meaning it's robust to any price impact model. Anyhow, that was it. Yeah, essentially the conclusion is don't throw away your observational data. Use randomized data because you can't do anything without it, but don't throw away your observational data. Try to combine the two as intelligently as possible. Yeah, thank you.
Are there any questions? Yeah, there. Any questions?
Sorry, I have a question. So you gave the motivation that there is some correlation between alpha and delta P that's not captured in the OLS model. So why, can you compare this, for example, with the two-stage least squares approach, where, for example, you have the correlation between Q and alpha, due to which you have a bias estimator. So if you chose to first regress Q and alpha, get the estimated Q, and then regress F of Q onto delta P.
Absolutely. If you have access to alpha, you should do that. So my argument isn't that this regression is biased, it's that you don't observe alpha, either because you're a broker and you literally aren't given the alpha, or because you're a fund and you can't historically reproduce the alpha. Does that make sense? Or again, as Rama said, like there's a distinction between predicted alpha and historical alpha. But if you have access to the alpha, which we have in our ground truth simulation environment, we can do that, and we see that that works. But my main motivation is that you don't have access to the alpha. But I agree, a two-stage OLS would solve that if you had access to, if you had full information.
Makes sense. Thank you.
No problem. It's a good question.
Any more questions? Ooh, well, you're going to have to pass that through.
Thank you. I would like to go back to your toy model at the beginning, where you were explaining the sort of causality, action and reactions.
Yes, which is very criticizable.
No, it's what I mean. This is not a criticism, it's just you are assuming, I guess, that there is no option trader in this model, because if there was an option trader, then the price will also impact the orders queue. For instance, this is there is a series of papers on a phenomenon which is quite rare but real, which is called stock pinning. When there is a large open interest on the strike and you're close to maturity, then in fact the action of the hedgers is going to pin the stock at a certain level. So so here you are implicitly assuming that there is no option trader, in fact.
Yes, or I'm assuming that the broker knows which flow is delta hedging flow versus pure alpha driven flow.
Is it possible to know that?
I don't know. I'm saying, yes, I'm making assumptions here on the nature of the client.
Okay.
And to Rama's point, you can always extend them all if you have a better representation of causality here. And what I mean by causality is you know what drives the trade. Here I have a very simple toy model. It is a pure alpha impact model with no crowding. So no other people trading in the same, using the same alpha. You could add crowding. You could add, as you said, like unfortunate feedback loops the other way. I'm not sure if the model stays identifiable. So that's a different technical issue. But yes, you could add more nodes to the graph, more links, and it would be an interesting problem.
Noted, thank you.
No problem. So this is not a complete, well, the methodology is general, the model is not. You need to adapt the model to the causal structure you believe. Yes?
Yeah, I've even more basic question. So your problem is to disentangle alpha and impact, but you seem to assume that it's trivial to disentangle both of these from epsilon, the thing you put nicely in the end.
Yes.
So in your simulation experiments, obviously it's trivial because you simulate independent IID noise, you add it, so the epsilon will average out by simple regression. But in fact, we don't know what, I mean, In fact, it's unobservable. The only thing you observe is the sum. And I never quite, I mean, I understand why people write this decomposition because that's what they're taught in finance courses. There's something called alpha, but for me, it's just a pure figment of our imagination. What is alpha really? Is it distinguishable? I mean, there's a market move. So
well,
I trade, you trade, everybody trades, market supply and demand aggregates and moves the price. What is this decomposition? And why is there such a decomposition anyway? Because in your experiments, alpha is random.
Yep.
All alpha generators generate a random alpha signal.
I agree.
So it's alpha t, and alpha t is really has a very complex dependent structure in time. What is the epsilon? Is it independent from anything? I have no idea.
So I agree with some of the criticism. Let me push back on some of the other. Let me try to be hopefully as precise as possible. But thank you for the question. It's if you're on the client side, so I agree that the broker never gets access to alpha, never gets access to epsilon. So there's a difficulty in expressing this exact equation. But the client knows which alpha triggered the trade. They have features, they combine them, and that creates a signal. That is what I call alpha.
That's the predicted.
That is the predicted alpha. Now, to your point,
What even is realized alpha? It's defining it is
it's very difficult. Yes.
Ambiguous.
Yes. So, do you agree that I can write this equation for the predicted alpha? The problem is then epsilon has some of the realized alpha.
No. That's the realized price move. So
yeah, but then you're just saying that the gap between the predicted alpha and the realized alpha is hidden in epsilon. That's all I'm saying. So epsilon now has some of the realization. So either I can write impact plus realized alpha plus epsilon. Epsilon is truly independent of alpha, or I can write impact plus predicted alpha plus epsilon, but epsilon is now not independent of alpha anymore because there might be some bias in my prediction. Does that make sense?
Okay, but then the epsilon is your forecasting error.
Yes, but it is I am making the assumption that the client's forecasting error is independent of their alpha, meaning that they have a properly calibrated alpha, which is a optimistic assumption. Not all clients get their alpha signal right, but that is implicitly what I'm assuming. Does that make sense?
Well, I'm not sure because Q only depends on the predicted alpha.
100%.
Okay, so there has to be a predicted alpha in the equation. It's Q of predicted alpha.
Q of predicted alpha.
Then what's in front? I don't know. You didn't define it precisely. I don't know what's outside the F of Q.
Okay, so then I think the equation that you do agree with is this plus realized alpha plus a completely independent epsilon. Do we agree with that?
Well, if you have realized alpha, what's epsilon?
Then epsilon equals 0, right? So that's another way to define it. Yes. So if I do this with realized alpha, you agree. Okay. Now I'm saying predicted alpha, realized alpha equals predicted alpha plus epsilon. Now I'm making the strong assumption that predicted alpha and epsilon are independent, which is essentially assuming that the client correctly calibrated the alpha. Then I get this equation and everything is consistent. Now I agree that it is a strong assumption and it seems that that's the one that you are disagreeing with. But in theory, I can write this. If realized alpha equals predicted alpha plus epsilon with alpha and epsilon independent.
So if the client is not extremely smart and their model is not well calibrated, are you overestimating impact or underestimating impact? What's the story?
I think you will be underestimating impact. Yeah, you will be underestimating impact because collinearity will drop if their realized alpha is lower. Like the hypothetical scenario where the alpha is completely wrong, has zero correlation with realized alpha, then the price impact estimate will be correct again. Yeah, it will be correct again.
Here's the situation. Let's say the client ignores some signal.
Yep, 10% of their signal.
Yeah,
yep. Then the bias will reduce by 10%. So my 30% bias will go down to 27% bias.
Okay.
Does that make sense?
Okay.
But to your point, that is not observed, definitely not observed by the broker. The broker doesn't know, A, the alpha of the client, nor the performance of the alpha of the client, like how correct or incorrect the alpha is. Again, we can do that in our simulation environment.
maybe a last question, and then we take it to the drinks. All right.
Yeah, I have a question on, like, say you do have access to the historical alpha.
Yep.
But that was the predicted, right?
Yep.
Not the realized. So one thing you could do would be regress f of q against delta p minus alpha. But in this case, would you rather use the predicted alpha, or would you actually think it's better to regress first the predicted alpha against the whole move, to get an estimate of like how much the alpha actually realized, and then subtract it to delta p? Say, because often when you first fit your alpha model, you think, oh, maybe this is going to realize 1% or something like this, but of course you overfitted on a period, so maybe actually only half of this prediction is going to realize. Are you accounting for do you think it's better to account for this difference in predicted versus realized? Or
if you believe that your predictor is correctly calibrated, then there's a direction. If you believe that alpha is independent of epsilon, so your predictor is correctly calibrated, then I think you want to subtract it to get a tighter confidence interval. But that variance reduction is because you believe that to be true. Otherwise, you don't want to do that. I don't know if this answer helps you, but it is very much a similar question as before. Like, if you have access to the alpha, in this case the historical alpha, you can do a two-step regression. Completely agreed. You always want to use the predicted alpha, not the realized alpha, when you do the regression against Q, because that's really what drives Q. So meaning, again, back to Rama's point, if I did have a graph with realized and predicted, it's the predicted one that goes to Q. So that is definitely the regression I want to do. Whether you get to subtract the predicted one from delta p, essentially calibrating alpha realized, the ratio between alpha predicted and alpha realized depends on your beliefs on the correlation structure between alpha and epsilon. And so if you have no knowledge, then you shouldn't do it. Then you should be doing the two-step regression naively. If you do know something about the correlation structure, especially if it's independent, if epsilon and alpha are independent, then you can do that just to get some variance reduction. Did that answer your question?
Yes.
And so maybe in terms of causal inference, what that means is you're making an assumption on the direction of the link between alpha predicted and alpha realized. But if you don't have any information about that correlation, don't try to do anything fancy. Only if you believe something about that. And you can try to use randomized experiments to figure out that direction, but that's a separate story. Whenever you either have to believe a certain direction in a causal graph, or you have to randomize to estimate it. Did I answer your question?
Yes.
Thank you. Thank you for the question.
All right, so I guess then any more questions should be directed to the speaker at the drink reception. You can also go to the book. Let's thank the speaker again.